So then I would like to introduce Andy Bricane. He's going to be presenting the white paper in the Processes and Best Practices track, 13 Reasons a Cost Estimate During Concurrent Engineering Study Could Go Wrong. Andy?
Okay, thanks Megan for the introduction, and thank you all for joining today. As said, today's presentation is about the 13 selected reasons, let's say, why a cost estimate prepared during a concurrent engineering study still could go not as good as expected, maybe. And I wanted to share some experience and observations I've made during several space system studies within our concurrent engineering facility. And the talk is basically a compilation of lessons learned described with a slightly different view, with the aim to raise awareness that even while using very efficient systems engineering methodologies, things still could go wrong. And I wanted to make it also a bit funny sometimes, so let's see if I succeeded. So what can you expect today? The presentation is basically divided into 3 parts. First, a general overview in which I want to introduce me, my working environment, and also to provide you some brief information about concurrent engineering in general, and also how it is applied to DLR. Then we go through the 13 reasons, or sometimes also called problems, why a cost estimate can go into the wrong direction. And of course, we'll finish with a brief summary and conclusion, including some lessons learned and recommendations. Okay, who am I and where am I coming from? So by training, I'm a systems engineer, so I'm rather from the other side, the technical and engineering one. But I lately moved more and more into the cost estimation domain. More than a decade ago, I was heavily involved in the buildup of the DLR Concurrent Engineering Facility, also so-called CEF, which is an engineering environment in which all relevant people, domain, subject matter experts come together to work simultaneously, for instance, on the design of a space mission or system, particularly during the pre-development phase. But more details with that later. Personally, I participated in approximately 50 studies in different roles, such as system engineering, team leading, or moderating, and as just said, more and more also cost estimation. And projects which I had the luck and honor to participate in include, for instance, the mascot landing package, which ended up being part of the JAXA Hayabusa 2 mission, which landed on Comet on October 3, 2018, which was German Unification Day, basically. And since 2 of my research interests are also engineering processes and human interactions, I sometimes feel inclined to compile such observation-based papers to look not only on the technical side, but also on the people-related aspects. A few words on the German Aerospace Center, or in short, DLR, for those who are not fully aware of this organization. Here's a map of Germany with all DLR sites and centers presented. The number is constantly growing. DLR is somewhat similar to NASA, and but smaller, of course, and comprises the German Space Administration, which is actually only a small part of it, and many R&D centers dealing not only with space, but also aeronautics, transportation, energy, digitalization, and security. We have more than 9,000 employees, more or less, and about 150 of them are sitting here in northern Germany, in Bremen, where the Space System Institute is located. And this place also then hosts the Concurrent Engineering Facility, which looks basically like an operations center, but it's mainly used for mission definition studies and not at all for launch or satellite operations. Not all of our projects use the CF, but many do. Several of these studies aim to investigate future potential missions, to identify, for instance, feasibilities or come up with a preliminary design. Some projects end after such a study, since they lost competition against other missions. Some end due to lack of funding. Others are put on hold because they're too fancy to realize right now. But some turn into reality, such as the presented here, AESAT, the Eurocropus compact satellite, or the just mentioned mascot landing package. But well, why setting up a CF, and also why using it? As many others did before us, especially in NASA and ESA, we also wanted to reduce the, let's say, typical communication barriers, which are unfortunately standard during regular office-to-office communication. There's also plenty of definitions about concurrent engineering as applied in space engineering, but in short, it's no magic. The idea is essentially to put everyone into one place, co-located, or these days maybe also virtually, and establish a structured and moderated communication process in which all subject matter experts or domains should mutually exchange their design progress to the entire team. It also facilitates parallel working while maintaining a clear share of responsibilities, and it's very useful in early stages, but can also be applied to later phases to a certain extent. And well, yeah, why are we doing this? As you know, space systems tend to be very complex, often unique products. They're also comparably expensive. And to build the product right, and also actually to build the right product, you should involve everyone in the design process right from the start, and make sure that there's a common understanding and also a common data set to be used by everyone. And yeah, in the end, it all comes down to communication, which then leads to a reduction of time and costs and increased consistency, less mistakes, and also a nice side effect, mutual education. So you learn a lot from others. On our side here at DLR, it is done by considering, let's say, the so-called 4 major elements or lags of concurrent engineering, which is the people, of course. It's the most important one. It includes the customer, the design teams, and everyone who has a relevant stake in that mission. It's supported by a guided process, which is managed by the so-called team leader or moderator. It makes use of an infrastructure. In our case, it's the CEF. And also very important, a central data model, which is a tool or software which acts as a single source of truth and ensures a smooth data exchange amongst the disciplines. The CE study itself, which on DLR side usually lasts about 1 full week, so let's say average working style, is the central part of the overall study or overall activity, which is framed then by an initiation and preparation phase, in which expectations, requirements, and first design options are defined by the core team, not to waste time of, let's say, everyone else, and also by a later post-processing phase in which the CE study results are harmonized and documented then. The study phase itself consists of several plenary sessions where the entire team participates in the discussions, and also so-called offline sessions during which the team or the team members can work on their own design, do their homework, so to speak, or discuss particular issues and traits in smaller groups. For the data model, there's plenty of options. There's commercially available ones, company-tailored ones, some provided by agencies, sometimes self-made in Excel or using more sophisticated software. But the overall goal for all of them is to ensure that everyone works with the latest set of data and that you have basically also simultaneous access to that data. Of course, we're not the only ones at the spacecraft crew with such an environment. There's plenty of other concurrent design centers worldwide with industries, agencies, R&D institutions, and universities using them. And also here, the number is growing. This is a map one of my colleagues put together, which I'm allowed to share with you. I guess maybe some of you have already worked within such an environment or have at least heard of or seen one. Yeah, since every entity adapts the concurrent engineering methodology to their own needs, there's also many different approaches. We at DLR use it for several applications, let's say project stage-wise, very early, not so early, option selections, or let's say in-point design. But for all of them, we typically use or follow a 1-week approach with 5 plenary sessions, which often represent 5 design iterations. The European Space Agency, for instance, in their concurrent design facility, they are spreading the sessions over the course of several months, with sometimes having only 1 or 2 sessions a week, which gives them in total a bit more time. And there's, for instance, the NASA Team X, we're one of the first applying this approach at Caltech JPL, who do, from my point of view, super condensed 3-day studies with several iterations a day. And all of them have pros and cons in terms of required preparation status, tool or people availability, required skills, and so on and so on. And what I can say about our approach, it's very efficient. The people, particularly the customer, is usually very happy. But yeah, I have to admit, it's also very, very dense exercise. So how is cost estimating done in the concurrent engineering environment? There's also difference amongst entities. Some, of course, keep the results and the work in progress confidential. We, for instance, talk about it a bit more frankly and more transparent, since we're an R&D institute. But even within one company, details of the process vary depending on the team, the partners, project type. But yeah, for all of them, the goal is and to provide a realistic and robust cost estimate, having all programmatic and technical aspects considered. And the general working rules in the CEF, which is start simple, start with something, iterate, detail, and improve, can be translated to the cost estimator, such as start with rule of thumbs or first analogy examples, keep an eye on the latest programmatic and technical agreements, start estimating user tools, update your outputs when necessary, investigate if several cost methodologies may be combined for cross-check, for instance, or for interpretations of the other methodology, and of course, talk. So be involved in discussions to avoid bad surprise in the end. And the important source of information on top of all the talking is the central data model I just mentioned, where we here use the virtual satellite one. It's an internal development. Moreover, at DLR, the tools we now, or also in the past, have used include, for instance, a small satellite cost model provided by the Aerospace Corporation, some internal ones, tools, CRs, but also commercial tools, and very soon also the latest provided Excel tools from NASA called the PCEC and the Mission Operation Cost Tool. So let's go to part 2. This is the overview of the 13 reasons, which we will go through now. They're not necessarily all limited to the concurrent engineering approach or environment. Neither are some problems solely limited to the cost estimator. Also, clearly, most of them are intertwined and interdependent, and there's by far more issues which can arise based on different experience people have made. Some also very obvious, and maybe there's sometimes not much you can really do about it. But the key message I would like to bring across is the awareness. So you have to know your enemy. So the first one is wrong expectations. This is mainly related to the customers or the major stakeholders, because depending on their background and interest, the expectation of the study outcome could be significantly different from person to person. Depending who the customer is, a project lead, a department head, or a business manager, they have, of course, different objectives. Maybe it's just a cost comparison, a detailed cost breakdown, or just a ROM idea of the cost, or something more elaborated. Normally during the preparation phase, it should be already clarified what can be done or not. But once everyone is in the same room and the study starts, I observe that the opinions might change a lot. And in most cases, all people in the end want to have a single number to take home. So let's say this costs 100 million euros or dollars. And sometimes even before the study starts, although the design information is completely immature at that stage. There's also often the desire for bottom-up estimates or engineering build-ups. But besides the, let's say, data availability or non-availability for such bottom-up estimates, the time needed to actually set up such an estimate is totally underestimated. There's often the understanding that everyone adds their input and le voila, here's the results. Of course, this can't work. Here you see, I guess some of you are familiar with that, an example of the NASA cost estimation process. And well, during the preparation phase, you clearly need to carefully discuss what can be done, what can't be done, and you should repeat that during the first study days again. So how to tailor the process, this is just an example here. Where's the limits and why? Where can we set the focus, either on spacecraft or rather the operational side? What's the cost approach? Are we going for design to requirements or design to cost? And of course, what can or shall be communicated to the outside, or just what has to stay within the team internally? So the next issue is a international multidisciplinary team. This actually a twofold problem. First, especially in DLR and European entities, there's many nationalities within the teams. In our institute, for instance, we have 150 people. We have also 25 nations represented. This is a strong boost of creativity, I have to say, but also it comes with the burden of having to deal with different backgrounds, different personalities, communication styles, and experiences. This really requires an experienced moderator and or makes them really mandatory, I think. The second aspect is if the outcome of the study includes also a project planning and not only a technical assessment, as it is the case, for instance, for a bid preparation or any other proposal activity. The question of the industry consortium enters the game. For example, in ESA-led programs, so the European Space Agency, a mechanism called geo-return needs to be considered, which means that financial contributions from the member state to ESA should go actually back into the national industry, which sometimes creates or leads to artificially complex organizational structures. As you can see, an example from a smaller science mission, actually. On top of this, also salary differences, are important, especially between Northern and Southern European countries. Although we have the same currency, most of us, it varies a lot, up to a factor of 3, comparing maybe Germany to Greece, or for example. And this requires careful assessment with respect to labor rates and costs, which is actually not often well reflected in most cost estimation relationships, so-called CERs, or any other models. So be sure who are you talking to, and of course prepare to consider the impact of different nationalities during the study, and also what does it mean for project implementation. Due to the nature of these concurrent engineering approach, there's different requirements to the tools which shall be used during the sessions. For the cost estimator, this relates particularly to the parametric tools, which are most prominently used at that stage, which means that they have to provide quick and robust results by using only a few inputs. It should be a clear application range defined, and also the clear and transparent ground rules have to be described. This is of course to support adaptation of estimates by having an understanding of what is already included and what not, to potentially adapt, for instance, inflation indices or currencies, in our case often from dollar to euros, or to adjust labor costs as just mentioned. There's some sub-problems, let's say, so unique and new systems with no or few data available. This maybe sometimes even questions the tool applicability. There's also not much time for homework, so if you have to do this in a week, you can't really develop your own CERs or do some bigger research on data. But maybe there's also no access to any tool, or there's no tool available at all because of the different types of, or maybe it's this very strange type of system, or you as a small entity do not have the resource to maybe acquire a commercial tool or to develop one on your own. So you have to think about tool adaptation also beforehand carefully, prepare different sources of data and kind of like, say, catalog style, fill your desk with all the different options, and don't also fear mixing cost methodologies. And it's kind of no-brainer, if tools are not really in line with the needs at all, don't use them, of course, and just put together what you have. So bad estimate is better than none. Specific, or let's say ROM costs. To have initial feeling on the ballpark cost range, using cost range is not uncommon. During a concurrent engineering study, there's typically a day 1 or even a day 0 task. Factors such as cost per mass, for instance, can be used as a reference for sanity checks or as an initial guideline, let's say. But well, these numbers are sometimes subject to misunderstandings. First problem, they barely state a fiscal year. So you have to really be sure from what literature or experience you have drawn this number. What does it represent? Is it old or outdated or quite recent number? Furthermore, these factors are very, let's say, easy to understand also for people who are not dealing with cost estimation. So some managers remembers that one different kind of satellite is $100 per kilogram, and then they start arguing with you about your assumptions and the cost rate. And of course, this have to clarify in advance. And one of the major problems I feel is that it's often unclear what exactly is behind this rate, so the euro dollar and the mass. As shown on the table here on the right, sometimes the reference really lacking precise information. What are we talking about? Are we talking about full project costs or spacecraft development cost? Does spacecraft development cost include actual payload or not? Are we talking about dry mass, wet mass, launch mass? So, and depends how you do the, let's say, the multiplication or differences, that it might be huge. In this case here, a factor of up to 3. So if you're inclined to use one of these numbers and walk into the lion's cage, which is the CF here in this case, and we're exposed to managers and other engineers which may have other ideas, then really assume the worst and involve everyone, be transparent, question every single number you have at hand, also from others, and then just go ahead. And the next problem comes along, which is the margins and contingencies. There's several standards out there which describing them in detail, and it should be clear which parameter should have which margin. So what kind of percentage shall I add, and what are the contingencies, and how would it evolve over different project phases. We always have the discussion in our CEF, but even with different opinions, we usually find a common baseline. So what's the problem? We do apply the ICEAA concurrent design facility margin philosophy. It's a well elaborated document and basically answers almost all questions. But when it comes to using the technical numbers as an input, for instance, to a cost estimation tool, a parametric one, for instance, then following questions remains. What data shall I actually use? To show you what I mean, here's a typical mass budget on subsystem level. Again, just an example. First, you see on the column which is marked with 1, the sum of equipment masses without any margins, so the so-called best guesses. Then we introduce the margins, and then in column 2, you can see the subsystem masses with the average design maturity margins included. And below, because you never know whether big requirements changes will occur, we add the 20%, according to our standards, 20% is margin to the dry mass, and then add propellant mass, and so on and so on and so on. But well, are these the right numbers? Since most tools are based on actual data, shouldn't you use then the more likely actual data, or the worst case as your inputs? This would then mean that you somehow should include the 20% as well, right? So, and the table on the right side, there's another column with a 20% system margin redistributed over all the subsystem masses, which is then a common input for the parametric cost models. And if this might be agreed, then the next question is where to put actually the data if several options exist. So if you take that column, where do you put it? There's a snapshot here from a commercial tool we're using. You somehow have to define in the beginning and make also clear during the tool selection process, which should take place prior to the study phase, the use and application of technical margins, not only for mass, but also for other parameter, and then how to use them amongst tools and models. And this should be clear, documented, and definitely agreed on, because during these rapid and iterative estimation loops within the concurrent engineering environment, these details may be completely overlooked in the end. Heritage and complexity factors. Sometimes they're part of a tool, sometimes they're not. Moreover, both might be very subjective and could be defined by several different parameters or design considerations, such as mass or number of units, type of units, maybe something like just software or mission aspects. On the right here, you can see an example of some compact class satellites launched by DLR or not in the last 20 years, which were supported by different partners, contractors, and also led by different teams or even institutes. For the next potential satellite now in that line, how do you, from technical and also from the cost side, assess how heritage and complexity is captured within the tool? Well, it's very early stage, and what level do you do this? So do you do this now on system mass, on subsystem mass? How do you basically reuse the experience from a project 20 years ago into a current project? It's a very, very subjective assessment. Again, no similar snapshot here. As said, some tools really account for this already, but surprisingly also the cost impact might be quite different. As an example, one parametric tool we use applies a factor in the 1.3 range when going from an average heritage of 50% to a full new system. Another one uses a factor of more than 2.5. That's quite a difference. In the end, so you need to know your CER sensitivity to really make careful assessments. Furthermore, also the input mask of the tool, sometimes they're asking for reuse percentages, other ones for percentage of new design, which is exactly the opposite. So you also shouldn't really get confused with that in the hectical concurrent engineering environment. So anyway, my experience is to save this rather, again, subjective adaptation to the last moment, and then until then make clear that this still needs to be accounted for, and that you assume or include this in your assumptions basically at the end of the estimation process. So here we are. It's basically the central problem, the price you pay, lack of time. It's actually not really a specific problem, but rather the mother of all problems. There's also not much specific to tell, as self-explaining. Lack of time is a problem for all participating domains, but the cost estimator, unfortunately, is one of the last in the data utilization chain, and you might get into trouble before the last study session starts and finishes. It's also clear that within 1 week, you can't really go through the full NASA, ICEAA, or DLR cost estimation process to full extent, which also might not be necessary given the early stage or the premature data. But well, there's still a lot of iterations you have to go for. On this slide, you can see another example. This time is an input sheet of the Excel-based small satellite cost model 2013. It includes here a self-made internal data input box on the lower right, which is basically a representation of the CEF central data model. And it includes also a total mass cross-check. And from there, the values are linked into the actual SSCM input sheet, and this might help to reduce some time, inconsistencies, or mistakes. It's just a very easy and simple example on how, let's say, the time problem could be reduced a little bit with very easy and simple tool adaptations to iterate as quickly as possible. So here's another lack, but compared to the previous one, this is clearly a general problem and not CE specific at all, I would say. So it's the lack of data. And by data, I mean both the technical reference information, especially in the early phases for new non-standard missions, and even worse, the cost-related information. In Europe, unfortunately, there's no, let's say, good database available to the public, such as the NASA ONCE database or the CADRI documents, in which technical and cost data for different projects and milestones are captured. So we simply just don't have that, or at least don't have access to it. There's also no public government accounting office reports, which help to get some real world data. Of course, big players such as in Europe, again, the European Space Agency, or industry players like Airbus or Thales, they have their own databases, since they frequently request and receive quotations and proposals, and have built also several spacecraft. But again, smaller companies and research entities, they need to rely on either the public information and or tools they somewhere acquired, which are based then on such data, which they do not have then by themselves in detail. Again, you need to do your homework beforehand, collect as much information as possible, and identify the information gaps, know the unknowns. This may help to put together a good estimate later by using kind of cost building blocks from both available and also applicable CRs, maybe also from other systems with similar equipment on board, which then can be used maybe in combination with an average cost breakdown percentage on subsystem level. So in this case, let's say mixing recipes with a bit of freestyle, so to speak, is one way to go. Of course, the technical data improves step by step during the design process, but given the short time and the dynamics of the iterative concurrent engineering approach, this rapid evolution might appear sometimes a bit chaotic. In this example, which I've shown here, it's basically a timeline of how the data evolves. It shows how the total dry mass, you see the bluish line, and the launch mass, which is a reddish one, purple reddish one, are evolving during a 1-week study. So different traits, decisions along the way, tool utilizations from the domains, design improvements, but also the attitude of the team members on how they use these tools or the central data model may lead to a constant up and down of the data, hopefully converging towards the end. The rapid data changes set one of the major requirements on potential cost estimation tools, which is to be easy to update. However, the cost estimator cannot perform all updates every time the inputs are changing, especially not in the beginning of the study. Furthermore, it also helps if the cost drivers from both technical side, but also from the potentially used CERs are already well known. It's good to know that what parameters to track and what to ignore at first. But ideally, the technical data would be automatically linked somehow to the cost methods and tools. But unfortunately, one additional problem is the disconnection to the central data model. One strength of Concurrent, but also any other model-based system engineering approach, is the use of a central data model, which acts as a single source of truth. At DLR, as I just said, we use our own Eclipse-based virtual satellite tool, which includes also several features, such as mass budgets, power budgets. There's different modes. You even can have distributed computer-aided design or functional diagrams. Of course, they also capture margins, but they do not, well, this tool does not, does trajectory analysis or doesn't come up with dynamic power file, and also, of course, no cost estimate. However, some data models enable interfacing to most prominent domain-specific tools, such as 3D design tools. In Europe, it's CATIA, for instance, or the well-known system toolkit, formerly Settle toolkit from AGI, which is used for orbital analysis. But for cost models, there's not much out there as far as I know. And this means you either need to include your own equations somehow, your database into the tool beforehand, which is a lot of work, and you never really know whether you will actually use that data. You maybe develop your own plugins, or you simply continue taking values from or to the central model manually, if you do this at all. This is, by the way, not only a technical shortcoming, but also a confidentiality issue, because sometimes people just don't want cost or sensitive information like that within a model. Well, better having a disconnected central data model than no common data model at all, as it's still the case for many, let's say, traditional project approaches where spreadsheets are sent back and forth still by email. But the cost domain just doesn't benefit as much from the data model as some other domains do, such as system, which make use of all the budgeting, or thermal or data handling, for instance, which also receive a lot of inputs prepared or pre-chewed already from that model. So if possible, if there's such a function exists, subscribe within the data model to the most relevant parameter to you, and also use very robust assumptions to basically cover or account for the initial changes or changes you might not be notified of because of the tool environment. And clearly, costs model-based system engineering is very, very underestimated. As I saw, there was also a paper related to that topic in the ICEAA workshop program planned, but well, since it was canceled unfortunately, it has not been presented. The next problem is the bottom-up estimates to be done during concurrent engineering studies. Obviously, since we are talking here about mainly early stage projects, it's typically not very suitable for early phase design, but often wanted by several of our customers because they just know the templates, they have to project planning, hand into the program management, and so they really would like to have the details very early on. As I also said, remember during the wrong expectations. But yeah, unfortunately, the effort and risk of compiling such an estimate is simply not understood sometimes. But that's also not the only aspect. Also, the subject matter experts, so the design team, they're also not often familiar with parametric estimates, and they also might not trust such tools and the data behind. So they have also more experience providing engineering build-up cost assessments for their own work package descriptions. But this then leads to several other sub-problems. If someone is not able to provide such a cost estimate on unit or on subsystem level, the estimate has gaps, obviously. If no model philosophy or test approach is defined, which is likely not the case in pre-phase A, how can anyone come up with a meaningful assessment on labor or material costs for the system qualification activities? Besides, there's also a strategic element. Some people tend to estimate at the very lower end to increase the likelihood of funding. Some others at the upper end to already claim their, let's say, comfortable budget, just in case the project continues. So doing these type of estimates, if this is really wanted or required, the way how people shall contribute to the assessment really needs to be commonly agreed on. To indicate some initial ranges or cost caps to the team members, preliminary and average cost contribution on subsystem level may be provided to the team by the cost estimator. And of course, do yourself a favor and do sanity checks with other methodologies anyway to identify big difference and potential mistakes or even flaws. 1 week of the highly intense design iterations is tough. So you should not waste time by optimizing the wrong end of the estimate. So let's have a look here at the standard NASA level 2 work breakdown structure. For a spacecraft design study, work packages 6 and 5, so spacecraft and payloads, usually receive the most attention, especially within a room full of subsystem engineers. There's not many tools which cover all work packages. But although, for instance, the latest version of a tool called QuickCost, developed by Hamaker, for instance, focuses on as well on work package 5 and 6, but it also provides average percentages, which can be modified for most other work packages too. And it also has the option to add, let's say, a factored or a manual input for work package 8, which is a launch cost here as well. However, an average mission still puts 60 to 80% of the total cost on the space segment, with all other work packages sharing the rest. But yeah, not all missions are average. For long duration science or interplanetary missions, the operations costs may be huge. And human missions clearly need much more safety and mission assurance than other missions might do. So according to my experience, as I said, that typically focuses on the spacecraft. Work which 3 and 10 year are clearly underestimated. You never really know the low or high percentage of the launch vehicle. How does that affect the overall assessment? And yeah, mission operation really depends a lot, but it's often not considered as much as it should do. And unfortunately, sometimes some workers are even completely neglected. This is the case often for science and technology efforts. So what to actually do with the data later on, and also for education and public outreach. So what can you do? Understand the mission, understand the drivers. Do not iterate yourself to death, figuring out maybe a mass memory cost while a completely new ground station has to be built, or while extreme testing is required for a super detailed interplanetary mission, for instance. So balance the details, and again, know your CR sensitivity in case parametrics are used. And yeah, don't forget the 80-20 rule. So finally, there can also be lack of acceptance. Due to lack of time, interest, or understanding of your teammates or managers, this may lead to some of these here presented statements, especially if you're not quietly sitting with the experts in their office alone, but with a bunch of technical people in one room altogether. A room which, by the way, in which fresh air is a limited resource at the end of each day. Furthermore, during our concurrent engineering study final presentations, which take place usually at the last afternoon, costs are typically presented at the end, if at all, but on our side mostly. This is because it's not so tangible as maybe a thermal analysis or a link budget, and hence may become subject to very lengthy discussions, which could really kill the agenda for the day. On the other hand, being one of the last to present, you will also find a very tired audience, which is not really motivated to listen to your assumptions and methodology selection process anymore. So this may lead to the feeling that no one else besides the manager really cares about the cost. During one of our last mission selection studies for the upcoming DLR compact satellite, I did the following, which I also can recommend if you've made some similar experience with respect to lack of attention. I will show you now here on the right side an in presentation basically, showing you 3 slides of one of the final presentations I did, or how I started them. Hello, my name is Andy. It costs 50 million euros as always. Thank you very much for your attention. Have any questions, please feel free. So I put a very ridiculously high number with no explanation at all. And in the end, everyone woke up. And then I started my real presentation, explaining everything, what methodologies, at which stage, and so on and so on. Where do I have the numbers from? And suddenly there was interest. So concurrent engineering studies are a great place, or better a great occasion to work together, to learn, but also to explain, educate, and clarify, and to play with the audience if needed. And if you did a good job and no one cares, well, just take it easy. So part 3. This is an attempt to put all of the discussed 13 issues or reasons or problems together and to see how they're linked. The color code indicated here on the top right should indicate whether I personally consider them as mainly CE study specific or rather as a general project issue which can arise during most of the other activities too. And ta-da, here comes the spider web. The results, which are highly subjective and of qualitative nature, is this. So you don't have to go into all the details right now by yourself. Although the lack of time, reason number 7, may be the biggest driver for most other problems, it somehow does not get most of the direct connections, no matter which I did. Within this assessment, it's rather the tool applicability, followed by our just mentioned mother problem, lack of time, and also the data model disconnection and rapid data changes. Plus, another, let's say, mini conclusion is that the problems 4, 5, and 6 relate to the specific costs, margins, and also heritage and complexity. It seems that they're rather isolated problems and compared to others, and also not very concurrent engineering specific, but general issues. In the actual paper, which you can also download, I've tried to cross-reference the major mutual influences within the subchapters, so you may have a look there for the details. Anyway, in summary, it can be said from my personal bias, but also long-term experience, that applying concurrent engineering for complex projects, in our case, space missions related, particularly in early phases, is highly recommended. It has a lot of good elements such as time reduction and also quality and consistency increase. But it needs to be understood that all people, including the cost estimator, are facing a couple of challenges. Amongst others, the low design maturity, tough schedule, many technical people, so not everyone understands the other people's work and decisions, and there's sometimes also very different cultures and expectations you have to consider. And as a takeaway message, so to speak, you could remember the 4 don't forget areas, which I abbreviated as impacts, covering ideally maximum preparation, awareness, communication, and transparent documentation, which means that you have to know your problem areas, you have to communicate everything what you're doing, and never expect the other ones understanding what you're doing, so and not vice versa. And document transparently what you've done, what you will do, and also what you not have done or can't do. So having said that, I hope I could provide you with some insights of the cost estimation problems within such a concurrent engineering environment, and maybe manage to bring 1 or 2 long forgotten items back to your mind. And I also hope that you enjoyed the talk. And I thank you very, very much for your attention. And I'm happy to take some questions. Back to Megan.
Well, I would say there have been no questions so far. So, you must, oh wait, we have somebody with their hand raised. I'm just gonna go for it. Brian Aposca, get ready to be on the line, sir. Brian?
Unmute.
I thought I unmuted him. Brian? Well, all right. Brian will have to email us his question. Rick Collins has a few things to say about the entire paper program altogether. So I'm going to unmute Rick here, and then that'll give everybody a chance to get their questions ready if they still have any. So Rick, are you here?
Thank you, Megan. Can you hear me?
Mm-hmm.
Excellent. So I've got a couple messages, one that I want to direct to Andy and then one to the audience in general. So first, Andy, thank you very much for the presentation today. Although you could not hear me laughing, I was laughing at different points. You were able to accomplish that objective. I was particularly humored by the point about how you get the audience's attention, and I agree entirely. There's something to be said about being provocative, and in many cases it's It's not conjured up provocation. It's reality. Boy, there's a big number here. So thank you for the presentation. Thank you even more so for making the time to write a paper. You know, it does take time. It does take effort. We're all busy. And, you know, as the president of the association, I think it's a really good thing for our membership to do. So thank you for that, and hearty congratulations on winning a Best Paper award. So thanks, and a final thanks for you know, being on the line. What is, you know, now probably, you know, 5 or 6 o'clock your time. So thank you for that.
Pleasure.
Yeah. So the other, you know, the message that I want to convey to the audience in general is as follows, and it's related to one of my thanks to Andy. That's, you know, if you're fortunate enough to have an abstract accepted for future ICEAA workshops, I strongly encourage you to go the extra mile and write a paper. You know, there's at least 3 reasons why I do this. One, you know, it qualifies you for one of the coveted Best Paper awards, and, you know, the accompanying recognition that comes both from ICEAA and hopefully from your employer and your colleagues. Second reason is because, you know, the process of authoring a paper will be an invaluable learning experience that could set you apart from your colleagues. You know, to be candid about this, I believe that effective technical writing is becoming a lost art, and I think an ICEAA paper is an opportunity to practice conveying your ideas in more than just the sound bites that are reflected on a briefing chart. So it's an area where there's much room for improvement, and I truly believe whether you're someone who's early in your career, middle of your career, or have been in the business a while, the ability to convey your ideas in full sentences is a real discriminator. And then third and finally, you write a paper. You are then an author whose work is publicly available to any and all via the excellent area and tech in ICEAA's website, where you can get to every paper and every presentation for how many years worth of workshops, Megan?
I'm thinking it's 12.
12. Yeah, so it's, you know, your work is there, and frankly, if you just, you know, you go out and Google, if anyone wants to go out and Google your name, it's gonna show up. That paper will show up just as your presentation would, by virtue of it being there on ICEAA's website. So anyway, I think that's the message that I wanted to convey to you. But yeah, it takes time. Yeah, it takes effort. But I think the payoffs far outweigh the cost of doing that. So Megan, is that a good segue for you to advertise next year's conference?
Yes, in fact, it's never too early to get your abstract in. We are already poised and ready to take them from you, especially since nobody really knows what day it is anymore. Better to let you know sooner rather than later. I've got the URL up there. So yeah, we hope to see a lot of folks putting abstracts in for the 2021 workshop in Minneapolis. And I have to say, Andy, you are off the hook. We did not get any questions come in. So for anyone watching who was a little shy and wanted to ask a question but didn't, Andy's contact information was a few slides ago, but you can also, of course, email the ICEAA office at ICEAA@ICEAonline.org, and we'll be happy to get you guys together. I look forward to hearing. Yeah.
One quick question. So in addition to Andy's paper available to everyone, this presentation is likewise going to be available to everyone?
Oh, yes. And the
Yeah.
YouTube recording of today's presentation will also be up on the website and on our
Cool.
ICEAA YouTube page. So special hello to people from the future who are in flying cars listening to us speak right now.
Okay.
Heavy. So thank you all for coming out today. Thank you all for listening. I look forward to hearing you next week at our at the next best paper presentation. Everyone stay safe, stay healthy, stay sane, be good to each other, and have a wonderful afternoon.
Thank you. Same to you.